Section 4.6, limits at infinity and asymptotes. We'll start this section off with an example. We're going to find the limit as x approaches to the right and left of 0 of the function 1 over x. We'll start by constructing a table for our left and right-hand limits. When we construct our table as we did in section 2.2, we'll be using the x values negative 0.1, negative 0.01, negative 0.001, 0.001, 0.01, and 0.1. Recall, we are not concerned with what's going on at 0, so we won't bother plugging 0 into the 1 over x function. Now to fill out our 1 over x values by taking each of our x values and plugging it into our function. And when we do, we get negative 10, negative 100, negative 1,000, 1,000, 110. Now we can evaluate each of our limits. As x approaches 0 from the right, our values are going from 10 to 100 to 1,000. So what's happening here is our function values, as we're getting closer and closer to 0, are increasing, and there doesn't seem to be a bounds to how high they'll increase. In fact, if you pick other values of x that are getting closer and closer to 0, such as 0.00001, you'll see that our function values are blowing up and getting larger. In previous sections, we said the limit does not exist. However, whenever functions increase without bounds, we do want to take special note of that. So since this is such a special trend, we're not going to just state the limit does not exist. We want to state a reason why this limit doesn't exist. Now, the problem is saying increasing without bounds is a bit too cumbersome. So what we're going to do instead is we're going to say 1 over x is going to approach infinity. And we're using the symbol infinity to represent that our function is increasing without bounds. On the other hand, as x approaches 0 from the left, we see we're going from negative 10, negative 100, negative 1,000. This time, our function is decreasing without bounds. Our function values are getting smaller and smaller and smaller, and it doesn't seem to be any cap at how small it can become. And just like with the increasing without bounds, in the past, we would say the left-hand limit did not exist. But because this decreasing without bounds is such a special trend, we want to state a reason why it does not exist. Since we used infinity to denote increasing without bounds, we're going to use negative infinity to denote that our limit is decreasing without bounds. We're using infinity and negative infinity not just to state that the limit does not exist, but we're describing the reason why it does not exist. When we're using infinity, we're stating that the limit is increasing without bounds. With negative infinity, we're describing that the limit decreases without bounds. This next slide goes over when we should use infinite limits. To start, whenever our function is increasing without bounds, whether x is approaching a from the right or to the left, that's when we're going to say the one-sided limit is infinity. On the other hand, whenever our function decreases without bounds, as x approaches a from the right or left, that's when we say the limit will approach negative infinity. Infinity and negative infinity are not numbers. Our limits here still do not exist. We are just describing the reason why they do not exist. We are describing the behavior of our function as x approaches a from the right or left. We can use infinity or negative infinity as the value of our limit for two-sided limits. When a function increases without bounds as x approaches a from both the right and the left, then we can say that the two-sided limit of f of x will approach infinity. When a function f of x decreases without bounds as x approaches a from the right and the left, then we can say the two-sided limit of f of x approaches negative infinity. Again, to make it clear, the limits still do not exist. We are just using infinity or negative infinity to represent the behavior of the function and describe why it does not exist. Now, without relying on a table or a graph, how can we tell if a limit is infinite? The way we can tell if a limit is infinite is as followed. If we're taking the limit as x approaches a from the right of f of x over g of x, it's going to equal a positive or negative infinity if g of x is approaching 0, but f of x is not approaching 0. And the same thing goes for the left-hand limits. X will approach a from the left of f of x over g of x will equal positive or negative infinity if the limit as x approaches a from the left of g of x equals 0, while f of x does not approach 0. The reason why these conditions indicate that our function is approaching positive or negative infinity is because as our denominator approaches 0, we are dividing by very, very small numbers in the sense of very close to 0. Since f of x is not approaching 0, then we're essentially doing some number divided by a really small number. This causes the fraction and the division to become very, very large, either in the positive sense or the negative sense. Now, if both the right-hand and left-hand limits are approaching the same infinity, then we can say that the two-sided limits is approaching that same infinity. The hard part is how do we determine whether it's going to be a positive infinity or a negative infinity? If we take a look at our first example, the limit as x approaches 2 from the right of x plus 1 times x plus 2 all over x minus 2 times x minus 3. The first thing we should always do when we try to evaluate a limit is to use direct substitution. And when we do the direct substitution, we get 12 over 0. This indicates to us our answer should either be positive infinity or negative infinity. Now we have to determine which infinity to use. To figure out which infinity to use, we do want to think a bit about sign rules and what our sign would be if we plug in numbers very close to 2 on the right into our function. We saw from our work, if I plug a value in that's really close to 2 on the right of 2, my numerator is going to be really close to positive 12. Now, what about the denominator? This is where we have to think about what the sign of our denominator will be if I pick a value very close to 2, but slightly larger than 2. Well, if I take a number close to 2 and subtract 3, that's going to give me a negative value. But if I pick a value that is slightly bigger than 2 and I subtract 2 from it, that difference will be positive. Well, if I do a positive value divided by a positive value times a negative value, that quotient is going to be negative. And we already know we're approaching infinity. So my limit as x approaches 2 to the right of my function is going to be negative infinity, thanks to my sine rules. As for our next example, we're going to have x approach 2 to the left of the same function. Our numerator, if we just plug in 2, will be 12, while our denominator will be 0. But just like above, I want to think about sine rules, but this time I'm working with values slightly smaller than 2. If I think of a number slightly smaller than 2 and subtract 3 from it, the difference will still be negative. However, if I take a number slightly smaller than 2 and I subtract 2 from it, this time I'm going to get a negative value. If I take a positive number and divide it by a product of a negative and a negative number, that product is going to be positive. So this time, our left-hand limit will approach positive infinity. You can use sample numbers if it helps. For example, if you pick a number such as 2.01 for the right-hand limit or 1.99 for the left-hand limit and plug them in, you will be able to see that our function would approach negative infinity and positive infinity respectively. For the next problem, we're going to take the limit as x approaches 1 of x minus 1 over x cubed minus 1. As always, the first thing we should do is the direct substitution. But when we do the direct substitution, we will obtain 0 over 0. 0 over 0 is not an indicator that our limit is approaching infinity. The conditions that we have listed above state that our numerator should not be approaching 0. Recall 0 over 0 is an indeterminate form. We don't know for sure if our limit is equal to a number or if it's going to increase or decrease without bounds. We cannot draw any conclusions. What we should do from here is use the strategies we learned in the previous section to rewrite our function, and then we can try to evaluate the limit from there. To rewrite our function, we'll start by factoring our denominator. Our denominator is a difference of 2 cubes and factors to x minus 1 times x squared plus x plus 1. Please see the previous section to refresh on the difference of cubes or the sum of cubes formulas. Now we can see the x minus 1s cancel, and we get the limit as x approaches 1 of 1 over x squared plus x plus 1, which is 1/3 by the direct substitution. So here we did get 0 over 0 when we did the initial direct substitution, but the limit was actually 1/3. In our next example, we have the limit as x approaches negative 1 of x squared minus 4x minus 5 all over x plus 1 cubed. Once again, if we do the direct substitution, we do obtain the 0 over 0 indeterminate form. So we do need to try to rewrite our equation. And we have x minus 4 times x plus 1 all over x plus 1 cubed. Now we can cancel out an x plus 1, and we get x minus 4 all over x plus 1 squared. If we tried the direct substitution again, we will get the negative 5 over 0, which does indicate that our limit does not exist. The question becomes, because this is a two-sided limit, can we say it approaches infinity or negative infinity? So to determine which infinity our limit will approach, we will analyze the left and right-hand limits. First, we'll look at the limit as x approaches negative 1 from the right. When we plug in values slightly larger than negative 1 into the numerator, it is going to be close to negative 5, thanks to our direct substitution work before. However, in the denominator, if I pick a number very close to negative 1 but slightly larger than negative 1, because of the squared, I know my denominator is going to be positive. What is a negative value divided by a positive value? That'll be a negative value. So our right-hand limit will approach negative infinity. As for our left-hand limit, just like in the right-hand limit, our numerator is getting closer and closer to negative 5. But because of the squared, when I plug in values slightly smaller than negative 1, my denominator will be positive. So I'm in the same situation I was in the right-hand limit, where I'm dividing a negative value by a positive value, so my limit will approach negative infinity. Since both my right-hand limit and left-hand limit are approaching negative infinity, I can say my two-sided limit also approaches negative infinity. It is very important to be careful of the 0 over 0 indeterminate form. Not only can we not conclude that the function is approaching a value, we cannot even conclude if the function is approaching infinity or negative infinity. It is very important anytime you get a 0 over 0, you remember that we cannot draw any conclusions and have to rewrite the function to a point where we can draw conclusions. Now we're going to discuss limits at infinity. Limits at infinity are used to describe the end behavior of a function. In other words, they describe what happens to the graph when we go to the extreme right or the extreme left. The right end behavior is the behavior of the function f of x when x increases without bounds. In other words, this is the limit of f of x as x approaches infinity. The left end behavior of the function f of x occurs when x decreases without bounds. In other words, this is the limit of f of x as x approaches negative infinity. One thing to note is that the limit laws that we learned in section 2.3 still hold if we replace a with positive or negative infinity. To help begin discussing limits at infinity, we're going to take a look at the limits of power functions as x approaches infinity. So here for these limits of power functions, we're going to let p be a positive value. The limit as x approaches infinity of x to the p will equal infinity. This is because since p is a positive power, as x gets bigger and bigger, no matter what p is, the value of x to the p will get bigger and bigger, increasing without bounds, which means x to the p will approach infinity. On the other hand, as x approaches infinity, 1 over x to the p will approach 0. This is because as x approaches infinity, x to the p we know is approaching infinity. So we have a denominator of a fraction that is growing without bounds. Well, the bigger the denominator of the fraction, the closer that fraction is to 0, which causes the 1 over x to the p to approach 0. When it comes to negative infinity and power functions, we do have to be a little bit more careful. For the next part, these only work if x to the p is defined for x less than 0. So for example, if p was 1/2, well, we can't take the square root of negative numbers. So the limit as x approaches negative infinity of the square root of x or 1 over the square root of x wouldn't make sense. But if we can raise negative numbers to the p power, we're going to have the following results. First, the limit as x approaches negative infinity of 1 over x to the p will equal 0. This is the same reason as why the limit as x approaches infinity of 1 over x to the p equals 0. If x to the p is positive when x is negative, then we have the limit as x approaches negative infinity of x to the p will be infinity. This is because x to the p is either going to increase or decrease without bounds, if you recall from the study of polynomials back in pre-calculus. But since we already know x to the p is positive, decreasing without bounds wouldn't make any sense. So here, x to the p would be approaching infinity. On the other hand, if x to the p is negative, then our limit as x approaches negative infinity of x to the p will be negative infinity because we'll have to decrease without bounds. Now we're going to take a look at some properties of infinite limits that kind of allow us to talk about infinity as if it's a number. One thing to keep in mind, infinity is not a number. It is to describe a behavior. But these help us think of infinity like a number. So here we're going to let a be a real number or positive or negative infinity. And we're going to let L be a real number. We're going to let f of x and g of x be functions such that the limit as x approaches a of f of x will be plus or minus infinity. And the limit of g of x as x approaches a will equal L. Our first property, the limit as x approaches a of f of x plus or minus g of x will equal plus or minus infinity. In other words, when I add or subtract a number from positive or negative infinity, that will not change the value of the infinity. Positive infinity plus or minus a number will still equal positive infinity. Negative infinity plus or minus a number will still equal negative infinity. Next, for multiplication, we actually have two rules. The limit as x approaches a of f of x times g of x will equal positive or negative infinity if L is positive. This follows the sign rules of multiplication. Here specifically, if I multiply positive or negative infinity by a positive number, I'm going to still get positive or negative infinity. Positive infinity times L will be infinity. Negative infinity times L will be negative infinity when L is positive. On the other hand, if L is negative, then the limit of the product will be negative or positive infinity. In other words, positive infinity times a negative number will be negative infinity, while negative infinity times a negative number will be positive infinity. Again, following the sign rules we've learned for numbers. Now lastly, the limit as x approaches a of g of x over f of x will equal 0. The reason for this is the numerator is getting closer to a finite value, while the denominator is increasing or decreasing without bounds. This is going to result in fractions that are getting closer and closer to 0 as f of x is getting larger and larger or smaller and smaller. So a number divided by positive or negative infinity will equal 0. One thing we do have to be careful of, since infinity is not a number, it does introduce quite a few different indeterminate forms. Examples of indeterminate forms with infinity are infinity over infinity, 0 times infinity, and infinity minus infinity. Anytime we do see these three indeterminate forms involving infinity, we do have to remember to rewrite our function to resolve these indeterminate forms. Now we're going to evaluate a few limits at infinity. A few of these limits can be evaluated if you recall important theorems and results from pre-calculus. For example, the limit as x approaches infinity of 3x squared minus 2x minus 1. We could evaluate this limit by using the leading coefficient test that we learned back in pre-calculus. But here we're going to look at a strategy of evaluating the limit where we will not have to rely on knowledge from pre-calculus. The general strategy is to factor out the highest power of x from our polynomial. For example, here, the highest power is x squared. So we're going to factor out the x squared from our polynomial. When we factor out the x squared, effectively what we're doing is dividing each term of our polynomial by x squared to figure out what's inside of the parentheses. So we have x squared times the quantity, 3x squared over x squared minus 2x over x squared minus 1 over x squared. From there, we can reduce, and then from there, apply our limit properties. First, the product rule, then a combination of the sum and difference rule and the constant multiplier rule. Now we can evaluate our limits. As x approaches infinity, x squared will approach infinity. As x approaches infinity of 3, well, since 3 is constant, then that limit will be 3. The limit as x approaches infinity of 1 over x, thanks to our limit of power functions, that'll be 0, along with the limit of the 1 over x squared. When we simplify what's inside of the brackets, we get infinity times 3, which is infinity. So we can see that the limit as x approaches infinity of 3x squared minus 2x minus 1 is infinity. In other words, our polynomial 3x squared minus 2x minus 1 will rise on the right, which is consistent with what we would see with the leading coefficient test. One thing to note, as we get more comfortable with limits, we're going to get to a point where after we factor, we'll be able to just jump straight down to the step where we evaluate each limit. In the next example, I'm going to start taking that approach, but just keep in mind that the background of what's going on are the properties we learned back in 2.3. Now we're going to take the limit as x approaches negative infinity of 2 plus 2 times x to the 5th minus 3x to the 7th. Just like in the previous problem, we're going to factor out the highest power of x, which here is the x to the 7th. And when we factor out the x to the 7th, we're going to divide each term of our polynomial by x to the 7th to figure out what would be in the parentheses. Then we can simplify. Now, as stated in the previous example, I could break this up even farther using our limit properties, but now let's just proceed to evaluate each portion of the limit. The x to the 7th, as x approaches negative infinity, will approach negative infinity due to our limits of power functions. The 2 over x to the 7th will approach 0. 2 over x squared will approach 0, while negative 3 stays negative 3. From there, we can evaluate 0 plus 0 minus 3, which is times negative 3. Negative infinity times negative 3. Negative times a negative is positive. And since we're multiplying n infinity with a number, we know the result will be n infinity. Since it has to be positive and n infinity, our answer must be positive infinity. Now we're going to take the limit as x approaches infinity of 3x cubed plus 4x squared plus 1 all over 5x cubed plus 3x minus 1. Here our function is rational, and rational functions are just the division of two polynomials. So what we'll do is we'll factor out the largest power of the numerator and denominator, just like what we did in the past two polynomial examples. In the numerator, the highest power is x cubed. In the denominator, it'll be x cubed. Now we can cancel out the x cubes, and now we're trying to take the limit as x approaches infinity of 3 plus 4 over x plus 1 over x cubed all over 5 plus 3 over x squared minus 1 over x cubed. Now we'll take the limit of each portion individually. The limit of 3 is 3. As x approaches infinity, the 4 over x and the 1 over x cubed will each approach 0. The limit of 5 is 5, while the 3x squared and the 1x cubed each approach 0. 3 plus 0 is 3. 5 plus 0 minus 0 is 5. So our limit would be 3/5. Now we're going to evaluate the limit as x approaches negative infinity of 4x squared plus 2 all over 5x to the 4th minus 3. Again, following the same strategy as before, we will factor the highest power out of the numerator, which here the highest power would be x squared. So our numerator will become x squared times 4 plus 2 over x squared. In the denominator, the highest power is x to the 4th. So our denominator becomes x to the 4th times 5 minus 3 over x to the 4th. Now we'll reduce the x squared and x to the 4th. And when we do, we get 4 plus 2 over x squared all over x squared times 5 minus 3 over x to the 4th. Now we can evaluate our limit. The limit of 4 is 4. The limit of 2x squared is 0. The limit of x squared will be infinity since x squared is always positive. The limit of 5 is 5. And 3 over x to the 4th is 0. Now here we are treating infinity as a number, but remember infinity is not a number. 4 plus 0 is 4. 5 minus 0 is 5. 5 times infinity is infinity. And 4 divided by infinity will be 0. So here, our limit as x approaches negative infinity of 4x squared plus 2x all over 5x to the 4th minus 3 is 0. Now we're going to take the limit as x approaches infinity of 6x plus 1 all over 4x minus 5x cubed plus 2 plus 5. Focusing on the 6x plus 1, we're going to start off by factoring out the highest power, which is x, and in the denominator, we'll factor out the x cubed. Now we can reduce the x and the x cubed. Now we can evaluate the limit of each term that is making up our function. The limit of 6 is 6. The limit of 1 over x is 0. The limit of x squared, since x is approaching infinity, x squared will also approach infinity. And 4 over x squared minus 5 plus 2x cubed would approach 0 minus 5 plus 0. The 5 at the end, that will approach 5. Now we can do the addition and subtraction in the rational part, and we get 6 over negative 5 times infinity plus 5, which is 6 over negative infinity plus 5, which is 0 plus 5, which is 5. So our limit as x approaches infinity of our function is 5. And lastly, we'll find the limit as x approaches negative infinity of x to the 4th plus 2 over 5x to the 4th minus 3. Just like in our previous examples, we'll factor out the highest powers in the numerator and denominator. In the numerator, we'll factor out the x to the 4th. In the denominator, we'll also factor out an x to the 4th. The x to the 4ths cancel, and we get 1 plus 2 over x to the 4th all over 5 minus 3 over x to the 4th. Now we evaluate our limit. As x approaches negative infinity, 1 will approach 1, 2 over x to the 4th will approach 0, 5 will approach 5, 3 over x to the 4th will approach 0. When we do the arithmetic, we get that our limit is 1/5. Now we're going to turn our attention to asymptotes. We were introduced to asymptotes back in college algebra when we discussed exponential and logarithmic functions, and we revisit them in pre-calculus when discussing rational functions and trigonometric functions. There are two types of asymptotes we're going to discuss: vertical asymptotes and horizontal asymptotes. First, for vertical asymptotes, if the limit as x approaches a from the right of f of x is infinity or negative infinity, or the limit as x approaches a from the left of f of x is infinity or negative infinity, then the line x equals a is a vertical asymptote of f of x. What this definition means is if our function on one side of a is increasing or decreasing without bounds, then there is a vertical asymptote located at x equals a. And keep in mind, vertical asymptotes are vertical lines. So we do have to write x equals a when representing the vertical asymptote. Horizontal asymptotes are used to describe end behaviors of the function. That is, if the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b, then the line y equals b is a horizontal asymptote of f of x. So if either the left-hand side of the graph or the right-hand side of the graph approaches b, then y equals b is a horizontal asymptote. Keep in mind from this definition, a function can have at most two horizontal asymptotes. Now we're going to identify the horizontal and vertical asymptotes from each of the graphs provided. For our first graph on the top left, we'll first locate the vertical asymptote. If we take a look along x equals 0, notice how as x approaches infinity from the right, our function is increasing without bounds. The fact that the limit as x approaches 0 from the right of f of x is infinity is enough to conclude that we have a vertical asymptote at x equals 0. A common misconception that is often formed about vertical asymptotes is that functions are always undefined at vertical asymptotes. Nothing in the definition states that f of x has to be undefined at x equals a in order for x equals a to be a vertical asymptote. So the fact that our function is defined at x equals 0 is okay. As long as one of the one-sided limits of 0 is infinity or negative infinity, then we have a vertical asymptote. Next, we'll find our horizontal asymptote. Horizontal asymptotes describe the end behavior. Looking at the graph, we can see that the right side of our graph is approaching the x-axis. This tells us that the limit as x approaches infinity of f of x is 0. So the line y equals 0 is a horizontal asymptote. Another common misconception that is often made about horizontal asymptotes is that functions cannot cross a horizontal asymptote. That is incorrect. Nothing in the definition states that a function cannot cross a horizontal asymptote. Also, a common misconception is some people believe that both ends have to approach the horizontal asymptote. That is also false. The definition states only one side has to approach the horizontal asymptote, not both sides. That misconception is often formed because that is a special feature of rational functions only. So here, our vertical asymptote is x equals 0, and our horizontal asymptote is y equals 0. Next, we'll take a look at the graph at the bottom left. On our graph on the bottom left, notice that the domain is -1 to 1, while the range is 0 to 1. Well, if the range is 0 to 1, that means there's no location of this graph where we're increasing or decreasing without bounds. Since our function cannot increase or decrease without bounds, that means there is no vertical asymptote. But what about a horizontal asymptote? Well, in order for us to have a horizontal asymptote, we need to be able to take the limit as x approaches infinity or negative infinity. But since our domain is -1 to 1, then the limits as x approaches infinity and negative infinity simply don't make any sense, so they would not exist. So here, there would be no horizontal asymptote. Now we'll find the asymptotes for the graph on the top right. We'll start off with the vertical asymptotes. We can see here at x equals 2, our function is increasing without bounds on the left, but decreasing without bounds on the right. It doesn't matter that both sides of x equals 2 are approaching different infinities. All that matters is at least one side is approaching n infinity. So here, x equals 2 would be a vertical asymptote. As for the horizontal asymptotes, we can see that the right end is approaching 5, so y equals 5 is a horizontal asymptote. However, we have to be very careful. We also have to check what's going on the left end. If we take a look at the left end, as x approaches negative infinity, we can see f of x is approaching -3. So y equals -3 is also a horizontal asymptote. Make sure you're checking both the left and the right end behavior for your horizontal asymptotes. A function can have at most 2 horizontal asymptotes due to its end behavior. Also be careful with vertical asymptotes. A function can have infinitely many vertical asymptotes. See the tangent function as an example. Now for the graph on the bottom right. First, we'll look for the vertical asymptotes, but we're not seeing any locations where the function is increasing without bounds or decreasing without bounds. So this function does not have any vertical asymptotes. As for horizontal asymptotes, we can see that the right end is approaching 1. In other words, the limit as x approaches infinity of f of x is 1, while the left end is approaching -1. So our horizontal asymptotes are y equals 1 and y equals -1. Next, we're going to evaluate the following based on the provided graph. First, we're going to find the limit as x approaches infinity of f of x. When we're trying to evaluate our limit as x approaches infinity, we're trying to observe what our graph is doing on the very far right. We'll observe on the far right, our graph appears to be getting closer and closer to the line y equals 5. So as x approaches infinity, f of x will approach 5. Now for the limit as x approaches negative infinity of f of x, which means we're trying to look at what our graph does on the far left. Now, if we look at the far left, notice how our graph is oscillating. Now, we learned before that oscillation were an indicator of limits not existing. However, if we look very carefully at this oscillation, notice how the amplitude of the oscillation is getting smaller and smaller as x is approaching negative infinity. And it appears that this oscillation is dampening and getting closer and closer to the line y equals 2. Because the oscillation is dampening, our limit as x approaches negative infinity of f of x will equal 2. Now we'll evaluate the limit as x approaches -1 from the left. So we'll start by drawing the vertical line x equals -1, which we see here in green. Now as x approaches -1 from the left, notice that our function is getting closer to the point -1/6. So our limit as x approaches -1 from the left will be 6. Now we'll find the limit as x approaches -1 from the right. If we start from the right of x equals 1 and we trace, we can see that our function decreases without bounds. So our right-hand limit will be negative infinity. Next, we'll find the limit as x approaches -1 from both sides. Since our two one-sided limits are not the same, our two-sided limit does not exist. Lastly, we'll evaluate f of -1. To evaluate f of -1, we are going to find a point on our graph with an x-coordinate of -1. Looking at our graph, we can see the point -1, 5, so f of -1 will equal 5. Lastly, what are the vertical and horizontal asymptotes? To find our vertical asymptote, we do want to locate any vertical lines where our function is increasing or decreasing without bounds. While looking at the graph, we can only see one location where our function is decreasing without bounds, and that's at x equals -1. So x equals -1 is a vertical asymptote. As for the horizontal asymptote, we've determined earlier that the limit as x approaches infinity of f of x was 5, so y equals 5 is a horizontal asymptote, and since the limit as x approaches -infinity was 2, then y equals 2 is also a horizontal asymptote. Now we're going to find the vertical and horizontal asymptotes of the following functions. We'll start by finding the horizontal asymptotes. This is because in order to find our horizontal asymptotes, we're going to find the limit as x approaches infinity and x approaches -infinity of our function. We'll start with x approaches infinity. Just like in our past examples, we're going to factor out the highest power in our numerator, which would give us x squared times 1 over 4 over x minus 5 over x squared. As for the denominator, we are going to focus on what's inside of the cube, which is the x plus 1. So we'll factor out an x from the x plus 1, which will turn it to x times 1 plus 1 over x. And then we can cube the two factors. Then we can reduce, and then we can evaluate our limit. And we get that our limit as x approaches infinity is 0. So one horizontal asymptote is y equals 0. But we also have to check the limit as x approaches -infinity. Now, most of our work for the limit as x approaches -infinity will be the same for the work that we've just done. In fact, if we look at the work that we've just done, we didn't care about what x was approaching until after this step that I just highlighted. So all the work for evaluating the limit as x approaches -infinity will be exactly the same as when x was approaching infinity. Well, since we've already done it once, we don't need to do it again. Now we can evaluate our limit as x approaches -infinity, and we get 0. So y equals 0 will be the only horizontal asymptote of our function. Now we're going to find our vertical asymptotes, which means we're trying to locate where f of x is going to have a limit of positive infinity or -infinity when we approach that value from one side. If you recall from the indicators of when we have a positive infinity or negative infinity as the limit, they occur when the limit of our denominator is 0. Since our denominator is a polynomial, that means the limit of the polynomial is going to equal the function value of that polynomial. So to figure out our candidates for our vertical asymptotes, we're going to see where our denominator is 0. Since wherever our denominator, x plus 1 cubed equals 0, those would be the values where the limit is 0. Well, if we solve this equation, we get x equals -1. Now we're going to evaluate our limits from the right of 1 and to the left of 1. If either one of these two limits are infinity or negative infinity, then we conclude that x equals -1 is a vertical asymptote. If we try direct substitution now in either of these limits, we do get 0 over 0. So what we need to do is try to factor out the numerator and see if we can cancel out any common factors. We'll focus on the right-hand limit first. The numerator factors to x plus 1 times x minus 5. We can cancel out the x plus 1s, and we get x minus 5 over x plus 1 squared. If we try direct substitution again, we get -6 over 0. That is an indicator that our limit is either positive infinity or negative infinity. Since we're just trying to locate the vertical asymptotes, we don't have to distinguish if it will be positive infinity or negative infinity. This is enough for us to conclude that x equals -1 is a vertical asymptote. Since one of our one-sided limits was infinity or negative infinity, then we don't have to check the other side. That's because we only need one side to increase or decrease without bounds to have a vertical asymptote. So our horizontal asymptote is y equals 0, while our vertical asymptote is x equals -1. Now we're going to find the vertical and horizontal asymptotes of g of x, which equals x squared minus 3x plus 2, all over x squared minus 4x plus 3. We'll start by finding the horizontal asymptotes, which means we have to take the limit as x approaches infinity and x approaches -infinity. We'll start with the limit as x approaches infinity. We'll start by factoring out the x squareds. Then we can see the x squareds cancel. And now we can evaluate our limit as x approaches infinity. And we get that our limit as x approaches infinity is 1, which means one horizontal asymptote is the line y equals 1. As for the limit as x approaches -infinity, we can recycle our work for the limit as x approaches infinity up to the step that we just underlined. So copying the results from our previous work, we have that our limit will equal the limit as x approaches -infinity of 1 minus 3 over x plus 2 over x squared, all over 1 minus 4 over x plus 3 over x squared. Now we can evaluate our limit as x approaches -infinity, and we also get 1. So our function only has one horizontal asymptote, which is y equals 1. Now we're going to turn our attention to the vertical asymptotes. Just like before, we want to determine where the limit of our denominator is 0. Since the denominator is a polynomial, and the limits of polynomials are evaluated through direct substitution, this is equivalent to figuring out where our denominator is equal to 0. So we'll solve the equation to figure out the potential locations of our vertical asymptotes. And we get x equals 3 and 1 being the potential locations of our vertical asymptotes. So to test to see if x equals 3 or x equals 1 are vertical asymptotes, we're going to find the limit as x approaches 1 from the right and the left, and x approaches 3 from the right and the left. Starting with x approaches 3 from the right, when we apply direct substitution, we get 2 over 0, which indicates our limit is plus or minus infinity. So that is enough to conclude that we have a vertical asymptote at x equals 3. Since we already know x equals 3 is a vertical asymptote, we don't need to check the left-hand limit, and we'll skip straight to the right-hand limit of 1. If we try direct substitution, we do get the indeterminate form 0 over 0, which means we need to try to simplify our function first and then try to take the limit again. To simplify, we'll first factor. The denominator we've already factored before. Val factored to x minus 3 times x minus 1. As for the numerator, that factors to x minus 2 times x minus 1. X minus 1's cancel. And we have the limit as x approaches 1 from the right of x minus 2 over x minus 3, which now if we try direct substitution again, we get 1/2. Since this is not an infinite limit, we cannot conclude yet whether or not x equals 1 is a vertical asymptote. So we need to check the left-hand limit. For the left-hand limit of 1, simplifying our function will be the same as before. So we'll still simplify to x minus 2 over x minus 3. And if we apply direct substitution again, we still get 1/2. Since both of our right and left-hand limits are not equal to infinity or negative infinity, then x equals 1 is not a vertical asymptote. So our only vertical asymptote would be x equals 3. Now we're going to find the horizontal and vertical asymptotes of h of x, which equals x cubed plus 5x squared plus 6x all over x squared plus 5x plus 6. We'll start with the horizontal asymptotes, which means we're trying to find the limit as x approaches infinity or negative infinity of our function. We'll start with x approaches infinity using the same strategy as before, where we're factoring out the highest power of x from our numerator and denominator. And when we do, we have x cubed times 1 plus 5 over x plus 6 over x squared all over x squared times 1 plus 5 over x plus 6x squared. Notice that the 1 plus 5 over x plus 6x squared is a common factor of the numerator and denominator, so they would cancel. And then we can reduce the x cubed over x squared, which gives us the limit as x approaches infinity of x. Well, if x is approaching infinity, then x will approach infinity. Since our limit of our function as x approaches infinity is infinity, then we have not yet located a horizontal asymptote. If we apply the same work for the limit as x approaches negative infinity, then our limit as x approaches negative infinity of our function will equal the limit as x approaches negative infinity of x, which will equal negative infinity. Since x approaches infinity and x approaches negative infinity is not equal to a number, then there is no horizontal asymptote. Next, we'll locate our vertical asymptotes. Just like in our previous examples, we want to locate where h of x will have a one-sided limit of infinity or negative infinity, which means we're trying to locate when our denominator will have a limit of 0. Once again, our denominator is a polynomial, and polynomials are evaluated through direct substitution. So we want to determine when our denominator will equal 0. We have another quadratic equation, and when we solve it, we get that our candidates for vertical asymptotes are x equals -3 and x equals -2. Now we're going to evaluate our one-sided limits around -3 and -2. If we start with the right-hand limit as x approaches -3, through direct substitution, we will get 0 over 0. So we'll start by factoring the numerator and denominator. We'll first start off by focusing on the numerator. The numerator factors to x times x plus 3 times x plus 2, while the denominator factors to x plus 3 times x plus 2. The x plus 3's and the x plus 2's cancel, which means we're evaluating the limit as x approaches -3 from the right of x, which is -3. So this is not yet enough to conclude whether or not x equals -3 is a vertical asymptote or not. So now we have to evaluate the limit as x approaches -3 from the left. Well, if we plug in -3 like we did before, we still get 0 over 0. So we would reduce like we did before. And when we do, our function reduces to x. And if we evaluate the limit, we get -3. So x equals -3 is not a vertical asymptote. Now we'll turn our attention to the left and the right-hand limits of -2. If we try plugging -2 into our function, we are going to get 0 over 0. So we'll go ahead and reduce our function just like what we did for the right-hand limit of -3. And in both cases, our function will reduce to x, which means we'll get -2 for both limits. So x equals -2 is also not a vertical asymptote. So here are only two candidates for vertical asymptotes cannot be vertical asymptotes. So our function here does not have a vertical asymptote.